Welcome to physics class. We shall be discussing about the magnetic field pattern and the strength when the current is going to flow through a straight conductor. Let us start the activity. We need a straight conductor. Let us consider a copper wire with a better thickness. Let us name it as XY, which is connected in series with the ammeter and the battery. We need a variable resistance, and we will pass the conductor through the cardboard on which we will be observing the magnetic field pattern. Since the flow of convention current is from positive to negative, the current will flow through XY in this direction. Closing the plug key ensures the flow of current. These are the arrangements we are supposed to do before we start the activity. Let us sprinkle few iron fillings on the cardboard. On passing the current through the straight conductor, we observe there is a pattern being formed on the cardboard. We should gently tap on the cardboard. Then we get a clear picture about the pattern that is formed on the cardboard. We can observe that it is formed in the form of concentric circles. On the circles that are formed are having the common radius. It means they are concentric circles. You would have studied the concept of concentric circles. So the circles which are having a common center but different radii. This image in the right side gives you the clear picture that is going to be observed in detail. You can observe the formation of concentric circles that is formed on the cardboard, which is going to be placed around the current carrying conductor. Coming back to the working of the experiment. We all know that any conductor through which the current is going to flow through, around that there will be a magnetic field produced. Same way here also, around the straight conductor XY, there will be a magnetic field produced. What is a pattern? The pattern can be observed. It is in the form of concentric circles. So it is very clear from this activity that if the shape of the conductor carrying current is straight, then the magnetic field pattern is of concentric circles. So there are two more important observations also, which the students tend to overlook and which is the favorite concept again in your MCQs. Let us place a compass needle on the cardboard at point P. If it is placed at point P, you will have to observe the deflection. The deflection where it is going to point out towards the north will be showing the direction of magnetic field. Suppose I increase the amount of current flowing through the conductor XY, what will be the effect on the magnetic field needle and the pattern? There will be no change in the pattern, but the deflection in the magnetic compass needle will be more. So, if we increase the current, the deflection in the magnetic compass needle also will be more. What happens to the deflection when we decrease the amount of current that is going to flow through the conductor? The deflection will decrease. So it is very clear that when we increase the current through the conductor, the deflection also will increase. When we decrease the current through the conductor, the deflection will decrease. It means the current is directly proportional to the magnetic field strength. That is nothing but current is directly proportional to the magnitude of magnetic field. So this is the important observation we usually tend to overlook. The activity can be asked for 3 or 4 marks by keeping this as the key point. One more parameter we have to keep in mind is the distance of the magnetic compass needle we are going to change for different trials. Here, in the first row of trials, when we are increasing and decreasing the current, let the distance be same. Let us consider it to be same. Now, let us keep the current value as constant or same. If we increase the distance, what will happen to the deflection? Let us imagine we will place the compass needle somewhere near point Q on the board, that is little bit far than P. Without changing the current strength, we will observe the deflection of the compass needle which is placed in point Q on the board, which is a little bit far from P. Since we are increasing the distance, let us imagine we are going to place the compass needle somewhere here in point Q, that is far from P. Now the distance is increased. It is very clear. What about the deflection of the compass needle that is placed in Q when the current is same? It is observed that the deflection will decrease. What happens if we are going to decrease the distance? That is, if it is brought back to P itself, the deflection is going to increase. So from this trial, it is very clear that the magnetic field strength is inversely proportional with the distance. Let us recall the key points that we have discussed in this whole activities. The apparatus has to be arranged in the same way as discussed earlier. On passing current through the straight conductor, we observe the pattern of magnetic field will be in the form of concentric circles. Then the magnitude of the magnetic field will change on changing the current through the conductor. That is, if we increase the current, the magnitude of magnetic field will increase. We come to know that it is increasing as the deflection in the compass needle increases. If we decrease the current, the deflection in the compass needle decreases. Hence, we can conclude that the magnitude of magnetic field is directly proportional to the current flowing through the conductor. Now let us check how will the magnitude of magnetic field changes on increasing the distance. Let us place the compass needle at point Q, which is far than P. On passing current through the conductor, keeping the strength of the current same in both the trials, the amount of deflection produced in both the positions P and Q, we will observe the deflection that is produced keeping the current constant. When the distance is less, the deflection is more. That is, magnitude of magnetic field will be more. When the distance is increased, when the compass needle is placed at point Q, same current is flowing, magnetic compass needle will be placed at point Q. At that time, the deflection will be less. That is, increase the distance, deflection will be less. Decrease the distance, deflection will be more. That means the magnitude of magnetic field is inversely proportional to distance. That is, if we increase the distance, magnitude of magnetic field will decrease. So when the magnetic compass is placed at Q, the deflection will be less. When it is placed at P, since the distance is less, we are going to decrease the distance. At that time, the magnitude of magnetic field will be more. That is, the deflection will be more. If you remember these 3 points, you can describe the whole activity, and it will also be helpful to solve MCQ.